Okay, welcome to Perils and Perils of AI, Part 1. Dr. Zaiane is giving the main lecture today. I just have a few remarks on this guy, and he seems the battery life has been progressively going down, and he was really impressive before you guys got here. But anyway, okay, so the objectives of the lectures in general, to introduce you to basic elements of AI, machine learning, and data mining, to introduce you basic concepts of the influence of artificial intelligence on the exponential future, including the concepts of unfriendly AI and the technological singularity, to provide you with concrete examples of AI, everyday life, and in medicine. Now, AI may seem like just another subject, but it is likely the most important area addressed in this course. The technological singularity is crucially dependent on AI developments. Unfriendly AI may represent the greatest existential risk out there. AI is very important to the singularity, but that does not mean that all AI researchers believe in the singularity or hold the same beliefs. For instance, Dr. Zaiane and I probably don't completely agree.
On the when.
On the when, well, yeah. We both agree that it will happen, but not exactly when. You can read about AI in books. You can experience it firsthand, which is more vivid. It's amazing how much of a relationship you can strike up with the Sony Aibo robotic dog, despite the fact that the production ended in 2005. Imagine what they would be capable of doing today if the development had continued the past 15 years. So it's a popular part of the course, and this shows the various features of the dog. And we will charge him up during the lecture, and maybe he'll be more interesting afterwards. Now, in Canada, this product for consumers was remarkably unpopular. And because I'm a U.S. citizen, sort of transplanted here, I guess, I was interested in it, but eventually the only way to get one was to fly to the U.S., stay in a hotel in the U.S., until the package with the Aibo in it comes for me, and then fly back. Why is that? Because Sony has buying around rules where you cannot buy things from Sony US when most Sony products are sold by Sony Canada. So anyway, but in AI research, it was heavily used in robo-soccer and things like that, with competitions, really quite interesting. And the Aibo finds a charging station when the voltage is low, like now. And so I'm going to put him in the charging station, and he'll...
Normally it finds it by itself, but that's in there.
Yes, he can find it by himself, and with this feature can keep going forever. There was much less interest in Aibo in Canada than the US, and you may wonder who is this for? It's not for a child, because a child within about 30 seconds pulls the ears and tail off, and it looks completely stupid. So it really is a toy for adults. And what kind of adults? Affluent young women are even the men who buy them supposedly buy them mainly for the young women in their lives. So on. Most government investment in robotics in North America is military robots, whereas the investment in Asia is robots to take care of the elderly and household tasks. Most consumer developments in this area probably come from Asia. Blade Runner, the classical 1982 movie, part of everyone's consciousness in this area, but they were biological beings, sort of genetic engineering. They weren't silicon and circuit board based, whereas most other AI in movies, they are based on silicon and circuit board. So they were very different from the rest. That's really all I have for you, and now it's Dr. Zaiane's show.
I have to turn the other computer on.
Yes,
So,
so just, yeah. So,
That's why, oh, I need a password and stuff like that.
Yep, yep, university's gotten quite organized of that.
Where's the password? Would it imagine me? Yeah, it does. So, Dr. Solis brought his iBo. Unfortunately, it's not working because it's not charging. While this guy is waking up, I also have a patient here.
Yeah,
I have another iBo.
medical case.
And Dr. Solis mentioned the ears. Indeed, they can come off very easily, the tails and everything. But more than just the ears and the tails, actually even the legs can come off. And this was broken. So what do? You can't fix it actually. It's very expensive to fix it, especially nowadays.
Right.
So in this particular case, we put a pencil. And will it work? No, it doesn't, because there's a gate, how it works, how it walks, that is programmed inside it. And it's not based on this, it's based on another articulation, the joint that exists here. But we can use AI to teach it how to walk again, like we learn how to walk with helpers. Okay. So we use what we call reinforcement learning to teach it how to walk. I'll talk about reinforcement learning another time. Okay. It's actually a lot of fun. So we don't dump it. Oh, I shouldn't forget the ear. Okay, is it on still? Starting, I don't know, I'm sorry.
But it's
well,
headed in the right
no, it
direction.
is.
There we go. Yeah.
Let me ask you a question first. Recently I was reading an article in the Time magazine. Is it Time magazine, the Washington Post? I don't remember. But anyways, they were talking about these intelligent computers, and they gave a very interesting example, and I'll give a different example. Do you all know Archimedes? Archimedes? Okay. Did he have a smartphone? Did he have a smartphone? Why not? He didn't have a smartphone, and the smartphone didn't exist. Okay? So it's common sense to us. It's obvious. You ask a child that knows about history and knows about what a smartphone is, they will immediately say, well, this is a stupid question. Computers today are not able to understand that. They will go and do a search, and will come up with some answer. Here's a webpage about Archimedes, here's a webpage about smartphones. They don't understand that. So there's no, in that article they're talking about causality. So we have ways of doing inferences and logic, but it's not the dominant technique that we're using today, like deep learning. And I'll talk about deep learning and machine learning. Okay, so this is on. What do? Come up here. Use this guy, and I think it's this one here. What? Yeah, of course I want to open this file. My apologies. Okay. So this is first installment of 3.
Yeah.
What is it saying again? I don't like to record anything. I don't know what they install in these smart classrooms. They're supposed to be smart. Okay. So this is part 1, and I'll have part 2 and part 3. Part 2 will be on Thursday. Part 3 is after I come back from my trips.
1st, I think. Yeah, October 1st.
Yeah. So the goal is to talk about AI, and hopefully at the end of these 3 sessions you'll have a better understanding about what AI is and what machine learning is and the different techniques and the relationship to the singularity, the technological singularity, the impact that AI and machine learning will have on your lives. And I'm not joking. The fact that AI is already here and you're using it and you don't know. It's, anyways, but before that, I will start by talking about a kind of a motivating example. And this is a real example, and this is related to medicine. I'll talk about Ebola. Who knows about Ebola? The Ebola virus. It's not curable. It's very deadly. Currently there is an epidemic that they're trying to control. It started last year in the Congo, and it's been around since then. I mean, I think they had 300 something deaths. There's another one that happened in 2014. This is what I'll be talking about. That happened in Western Africa. So many countries in Western Africa, we had many people dying, many people getting sick, and they didn't know what it was. They didn't think it was Ebola, they thought it was cholera, because people had the same symptoms as cholera, vomiting, diarrhea, and all that stuff. And it's only months later that the World Health Organization realized, oops, this is Ebola, we have to treat it differently, completely different. It's not a bacteria, it's a virus, and it's spreading very fast. So we had Liberia, Sierra Leone, Guinea, Nigeria, Mali, Senegal, and more importantly to us, actually it started spreading to the United States, Italy, United Kingdom, and Spain. In the US, somebody died, actually. So today, when you have an outbreak like this, it's not localized, it very quickly becomes global. So this is the map of which countries, and why it is important. It's because people travel, okay, and it becomes very quickly becomes global. This is important, and then should I say something political here? Our neighbors in the south have decided to cut the funding in their research of Ebola virus, saying that it's not important. But actually, this map shows it's important not just for Africa, but everywhere in the world. Okay. So why am I talking about this in a course about AI? It's because when an outbreak happens like this, to better understand what's going on and better understand in the future how we can manage it and control it, the first thing they have to do is identify patient zero. Where did it start? And then understand why. Okay. So remember that I said that it took months for the World Health Organization to realize that this is Ebola. By then you had already thousands of people that were sick, and it wasn't just in one country, it was many countries. Okay. So they had to use techniques, sophisticated techniques, social network analysis, to finally build a tree like this and identify the original patient, a toddler that was dead by then. And when they went to the village, actually the whole thing was gone because they burned the house, they burned the tree, burned many things. The traces were gone. But what they realized is that, oops, no, that's not what I want to do. Emil was the patient zero. What they realized is that Emil was playing close to a tree that housed these fruit-eating bats. And that meant that these fruit-eating bats now are a reservoir for Ebola. A reservoir for Ebola, that means this is an animal that can have the virus, but not getting sick from it. And that's new news for them, it's new information, because in the past they knew that insect-eating bats were Ebola reservoir. Then they used machine learning. Machine learning is part of AI, and I'll talk about that later, to build models where they introduced, so they gave as input to these machine learning algorithms, they gave data about animals that they knew as being Ebola reservoir, and other bats and other animals, And they build these decision trees, and I won't go into details how they build it, but they build it and reuse it again until they finally identified the different kinds of bats that they didn't know before as being a reservoir, and actually they are. And then they remapped them on the world. So this is what they thought where the current reservoir lived, the bats. But when they mapped the new bats that now they suspect as being reservoir as well, they can see that there are many other hotspots. And interestingly, there are hotspots in places where it's not as common to have the Ebola. Ebola is mainly in Africa. So why is it that people are living with other bats that can be Ebola reservoir, they don't get sick, while in Africa they get sick. So that creates new hypotheses. So machine learning has been used not only to discover new information, but it has been used also to create new hypotheses for new research. Then, as I said, Ebola is not curable, but they are looking for treatment. And there are some, well, there are many databases of different compounds that people use to build these drugs. And they didn't know which ones, there are millions of these, they didn't know which ones actually they should use as anti-Ebola virus, which ones have this activity against the Ebola virus, and they use machine learning again to identify some compounds. And then when they tried them, they realized, particularly these three, that they were very good against the Ebola virus. So now we are using machine learning to also identify compounds that can be used to build drugs. So what is this machine learning? It's helping medicine in an amazing way. What is AI? What is machine learning? This is what I'll be talking about at a very high level. We'll go in more details next time. I'll explain why now. Why is it becoming even more and more important today? And I'll dive into precision health to show how AI and machine learning can help in medicine. And I'll give examples. So that's the plan. Okay, first of all, what is AI? Artificial intelligence. I personally don't like the term, because intelligence is intelligence. There's no real intelligence in artificial intelligence, but that's how we call it. Some people call it actually computational intelligence, or an intelligence that has been computed. But intelligence is intelligence. Anyways, artificial intelligence has been coined in the 50s. It's not new, it's very old. After the Second World War, people started thinking, what can we do with these machines that we built, these computers that we built to decipher enemy code and to calculate trajectories of missiles and stuff. Now we have peace, what can we do with these big machines? Okay. So they were thinking about using them for the common good, and some scientists said, well, actually these machines are amazing. These machines were big, like bigger than this room. These machines are amazing. They can do amazing stuff very fast. So they hypothesized that intelligence can be broken down into different pieces, and if you can program each piece individually and put them all together, then we can create a machine that is as intelligent as human. And that's what they called artificial intelligence. Now that was in the 50s, and at that time they believed it was possible. I mean, they were very convincing at convincing the decision makers in the government, and they were funded, and that's when AI started. And it was successful to some extent. How do they demonstrate their approach? Well, they said, for example, here's some games. You have to be intelligent to play these games. So if the computer can play these games and win, then the computer is intelligent. Make sense? For example, chess and other games. So that's where we started. And as I said, it was successful to some extent, but very quickly they realized the promises are not reachable. So this is talking about the 50s, 60s, Then there was a disillusionment, and people had kind of abandoned AI. The funding dried out. But some people continued stubbornly working on some part of AI. AI, there are many, many parts. One of them is, so as I said, there was optimism and all that stuff. One subfield of AI called machine learning. Some researchers were continuing to work on that, started having success in the 80s. So machine learning is about learning from training data, learning to do some tasks without being programmed specifically to do that. I'll show you some examples. And because, thanks to the success of machine learning and the success of other subfields like expert systems, there was a renewal in hope. This brought back some hope, and some very interesting applications were actually very successful. You know that the credit card you use, for example, today, when you use your credit card, there's an authentication that has to go to the central database, and it gives you the okay or no okay for that transaction. That authorization that is sent back to the merchant actually is using some machine learning to identify whether this transaction is fraudulent or not. Okay. And it looks at your purchasing behavior. So these are very successful applications. I'll show some applications later. And then a subfield of machine learning called deep learning started very recently, and that changed everything. Why? Because in some applications with deep learning, we were having incredible success beating the performance of humans. Okay. And I'll show you examples, as I said. So you have artificial intelligence, inside it you have machine learning, and inside it you have deep learning. This is a very important figure. I didn't build this figure, I actually stole it from NVIDIA, while I borrowed it. This is important because many people, even journalists writing articles and to the masses, they are confusing deep learning, machine learning, and AI. They're not synonymous. One encompasses the other. So the image that I want to show, this is not NVIDIA, this is me. You have the field of computer science. Within computing science, you have many subfields. One of them is artificial intelligence. Same thing as networking, high-performance computing, software engineering, graphics, databases, security, and all that stuff. These are all fields in there. I didn't make artificial intelligence bigger than the others, saying that it's more important. No, I made it bigger because I'm going to zoom in. Within artificial intelligence, you have many subfields. One of them is machine learning. But you have other ones. You have planning, knowledge representation, reasoning, computer vision, natural language processing. They're all part of AI. And again, it's not that machine learning is more important than the others, it's just because I'm going to zoom in. Within machine learning, you have supervised learning. I'll mention that later. You also have unsupervised learning, reinforcement learning, there are many paradigms for learning. And inside supervised learning, you have different paradigms. So deep learning is one of them. Okay? So what I'm saying here, the message I want to say here is that deep learning is a kind of supervised learning, which is a kind of machine learning, which is subsumed by AI, which is part of computing science. Okay. They're not at the same level. This is extremely important to understand. Okay, that's supposed to represent the brain. So when you read the newspapers, you see titles like this, AI market will be worth $60 billion in 2025. This is 5 years from now. This is huge. You see articles saying like, the one who dominates AI will rule the world. You know who said that?
Putin.
Putin, exactly. It shows you how important AI is. And why now the big powers are actually now racing to win this challenge. And who's currently winning?
China.
China. China's currently winning. And finally, the US is admitting it. So unfortunately, so this shows that how AI is very important, and you find it in all magazines, newspapers, whatever. People are flooded by this, but unfortunately we don't actually know what AI is, and most people get their definitions from science fiction movies. And unfortunately as well, these science fiction movies don't portray the real, what really AI is. They often show a very pessimistic view, them, the machine, against us, because it's sensational, because it attracts people, watch the movie, suspense and all that stuff. And this is something I don't like. It's not the machine against us, because as soon as we say machine against us, it's an enemy. We start becoming fearful, we hate them, we don't like them, we want to destroy them before they destroy us, all that stuff. It becomes an existential threat, and you certainly heard very famous people saying that the most important existential threat is AI. Before even the atomic bomb, before even anything else. I don't believe it, but that's what they say. If you want to know what AI is, this is the level of AI we reached, the smartphones. Smartphones have incredible, actually, algorithms inside them. And we'll talk about some of this stuff. But not Terminator, we're not there yet. And hopefully we will not get there. So here are some definitions of artificial intelligence. This is given by Marvin Minsky. Marvin Minsky was one of the pioneers in the field of AI. They started the first conference on AI in 1956, and he was the founder of the AI research lab at MIT. And he said artificial intelligence is the science of making machines do things that would require intelligence if done by humans. Another definition, artificial intelligence is discipline striving to get machines behave intelligently by performing tasks that would normally require human level intelligence. This means that actually we understand what human intelligence is, but we still are debating that. For me, artificial intelligence is just an enhancement of human creativity. What does that mean? It means that artificial intelligence is just a tool. We are building tools, more sophisticated tools, to help us do things that are more and more complex. Okay, I wanted to put two pieces of wood together. I got the idea of a nail, yeah, but I can't push it. I will invent a hammer. The hammer is not replacing me. Okay? I build the hammer to do my job better than what I would do it without the hammer. And that's how I see AI, and I'll show you some examples later. So it's an extension of ourselves. You probably also heard another term called data mining. Who has heard the term data mining? 3 people, 4. Okay. Data mining was actually very, very popular in business, and there was a lot of hype about it. Then it disappeared, particularly after 9/11, because people were associating data mining with government spying on us and things like that. So even companies stopped using the term data mining. They were using other terms like business intelligence and things like that. Data mining is coming back in fashion, even though it's overshadowed by machine learning and deep learning. Data mining is actually encompassing as well machine learning. So data mining is the process of discovering and extracting potentially useful and previously unknown patterns from large collections of data. And machine learning is using the same thing. We're looking at data. We extract patterns from the data that can be used to discriminate different classes. I'll talk about that later on. So that's what data mining is. The analysis and intelligent interpretation of large data in order to provide actionable knowledge for human decision support, or sometimes not just humans, but other algorithms also to make decisions. Okay. And data mining is it's at the confluence of many, many fields, among them AI. And that's why I say, oh, machine learning is actually doing that. This is important to know because all these terms are used often interchangeably, but actually they mean different things. You have to be careful. Okay, so you know a little bit about what AI is, and well, machine learning, I'll explain it later, but why is AI becoming important now? I just said that it started in the 50s. 50s, that's a very long time. Why is it coming back now false? Well, there are three major factors. One is the fact that today we have a lot of data, more data than we have ever had before. And actually, every year we have more data than the last 10 years. So every year we create more data. It's exponential, the amount of data that we're creating, and the amount of data that is available to be analyzed, and we extract these patterns to do something actually. The other factor is, I'll talk about this one first, we have more and more sophisticated hardware. I showed you the smartphone. The chip that is on this smartphone is more powerful than the big machines that governments used to keep secret. And now you have it in your pocket. The chip that I have on my smart watch is more powerful than the computer on board Apollo 11. The rocket, taking people to the moon, and now I have it on my wrist. So the high performance computing advanced at an incredible pace. And then we have new algorithms that can take advantage of that quantity of data and take advantage of these computers. So I'll give you some examples to really understand what really happened. Where's the data coming from? I'll try to go fast. We have many slides here. Well, you obviously know that we have a lot of data every single minute produced on YouTube, on Netflix, on Google, Facebook, all the social media. I'll pass all this. This is obvious. But people have tried to quantify it, just to make analogies so people really understand how impressive this is. Yeah, this is all different sources where it's coming from. Some estimates. 2011, the U.S. healthcare system apparently reached 150 exabytes, and soon will reach this zettabyte. What are these terms? They may not mean a lot to many people. So here's something to illustrate. And people wrote papers on that. This was in 2000, this is a paper that came out in 2007. So they said if we take, this is about, yeah, so this is the data that was digitized at that time. They said if we store them on CDs, you remember the CDs? If we store all this data on CDs, because people don't understand zettabyte, petabyte, all that stuff, so we say, okay, they take the unit CD. If we store them on CDs, and we stack these CDs one on top of each other, knowing that CD is 1.2 millimeter, we need enough CDs to reach the moon. That's in 2007. It gives you an idea of what is this quantity of data. Well, there's another paper that was written later on, and they said, well, that's nothing. They only focused, I think this was written in 2011, so 4 years after, and they calculated just the medical data in the US. Not all the data, just medical data. Don't put them on CDs anymore, put them on DVDs. They have a better technology, DVDs at that time. Then you reach the moon twice. This shows you also how fast this is growing. You all know about this. What is this? Micro SD card. You know these SD cards you put on your cameras. You used to put on cameras. You can extend the memory of your smartphone. Nobody has a camera anymore. Everybody uses a smartphone. Okay. 2005, the best micro SD had 128 megs. If 3 years later, 128 gigs. 2 years later, 256 gigs, it doubled. This shows you how fast this is growing. 2018, now we have 512 gigabytes. So we went from 128 megs to 512 gigabytes, so that's 4,000 times more data on the same space in 13 years. Okay, from 2005 to 2018, 13 years, we improved how much data we can put on the same space 4,000 times. Just keep that in mind. Now, another example. This is a picture taken in 1956. IBM is delivering a hard drive. You know what a hard drive is? Okay. This hard drive was 5 megs. I mean, a nice high-resolution picture takes more than 5 megs. That was a hard drive, 5 megs. This was a big deal. Even the captain of the Pan Am airline was there for the photo op, because it was a big deal, 5 megs. This hard drive, 5 megs, was costing $120,000, 1956. Last year, I bought this SD card, 64 gigabytes for a camera on a famous website, I'm going to name it, for $18. So from 64 gigabytes in here, how many times you can put 5 megs? Okay, this one was a huge filing cabinet. If I had the 64 gigs in 1956, it would cost me $1 billion. Not a million, $1 billion. It's inconceivable. $1.5 billion, actually. So that's an improvement of 76 million times in 62 years. So that gives you an idea about the data that we're storing. Now that we have the capability to store, as I said, I can put the gigabytes in this. It's free to store. Nobody deletes anything anymore. Keep all that stuff. High performance. So we're convinced about the data. We're storing a lot of data. It's cheap to store the data. What about high performance computing? What's the improvement we got? Today, my students are using GPUs. You know what a GPU is? What do you use a GPU for? Playing games. People who play video games, they don't just use the CPU, they use the graphical processing unit to do the graphics fast on the screen. So now we're using these GPUs to do these very powerful, sophisticated calculations, not to play games. My students are not playing video games, they're using it to do calculations. This GPU is about $1,000. And that GPU, $1,000, is equivalent to the Cray 1 machine, that a few years ago was $10 million. Now, I can have that Cray 1 machine, $10 million, that only a few countries had it, and few organizations in the States also had it, because of course it's very sophisticated. Now I can have it on a commodity PC at home. The change is drastic. Not convinced enough? This is a figure showing, in a logarithmic scale here, showing the best computers every year. So this is since 2013, they started keeping these statistics. I had this figure from last year, and they plot here, just look at the yellow one, the best computer that year. Okay? So here it didn't increase much, and then suddenly you have a very good, better computer, and so forth. This is the fastest computer today. Fastest in terms of how many floating operations that they can, floating number operations that they can do per second. Okay. So for many years, in 2016, the fastest computer was in China. with 94 petaflops. It costed $275 million. And finally in 2018, the Americans have now a faster machine. Is actually a collection of GPUs put together, the graphical processing unit, and they reached 122 petaflops in June 2018. If I zoom in here, okay, this is the kind of fastest phones we have today, approximately. We have the new version that came out, the iPhone X for the iPhone machines, the Apple machines, and the Android machines. The fastest one, when I did this slide, was the Samsung S9. Where does this machine that I have in my pocket fit in this list of fastest machines in the world? Well, it will be equivalent to the fastest machine in 1998 or 1997 that had about 1 teraflop. That machine, the ASCII Red, was the size of a tennis court. I have it in my pocket. Was how many millions? $55 million. I buy this for less than 1,000. It had 10,000 Intel Pentium Pro at that time. It was consuming enough energy to heat 800 houses. I'm glad it's not the case for the phone in my pocket. Well, here's the machine, and now there's the equivalent phone there. So I went from a tennis court machine to something that is in my pocket. So the improvement is phenomenal. Okay. So what's the difference between this machine in 1993 and this fastest machine last year in terms of speed? And remember, that's a logarithmic scale. So we are talking about 206,000 times faster. What does that mean? I try to give an analogy so you better understand how mind-boggling this is. If a human being was doing the same progress 206,000 times improvement, it means that my step, which is about a meter, that I did in 1993 when I did my PhD, when I was starting my PhD. Now, if I improved as fast as the computers, my step will be equivalent of 206,000 times 1 meter. What is that? 206 kilometers. One step, I would do 206 kilometers. So I would go almost to Calgary, one step. That's the progress that computers did. I'd be able to go anywhere around Edmond. What about the progress here? 4,000 times means 4,000 a meter, so that's 4 kilometers. One step, I would go anywhere like within Banff. I will actually leave Banff. This is the slide I was preparing when I was in Banff. If I use the same analogy for the progress in terms of cost for space to store, 76 million times. 1 meter, 76 million meters, is that what? Well, it's twice around the world. That's the kind of progress we did. Okay? And that's why what they couldn't do in 1956, when they were promising everything, they were promising the moon, they couldn't do it. But today we have something that is way faster, way more memory, way more data. Now we can do some of the things that they promised before. I want to talk a little bit about progress we did also in algorithm development. Actually, we are using the ideas that they came up with years ago that we couldn't implement because you didn't have the sophisticated machines, you didn't have all the data, namely neural networks that we call now deep learning. So I'll introduce you very briefly to this idea. This idea started in the 50s, where they tried to mimic what we understand about how the brain functions. So they said, well, the brain has these neurons. The neurons are connected with these connections. You have the dendrites to get information, and then you have cell body, and then you have the axon to send the message, and the axon connects to the dendrite of another cell, and so forth. So they created these artificial neurons, and then they put them all together to create an artificial neural network. So a neural network, you have these artificial neurons that get the input, and they spread the information to another layer of also artificial neurons. And these will spread the information to another layer until they reach the output layer. And we give them some information here, and then at the end we'll get the prediction at the output. And if we have the time in the third lecture, I will explain in more details how this works. So basically, what a neuron is, you have a cell that sums up connections that come to it. This is a vector with weights, so the connections are not all the same, they have different weights. I sum them up here sometime, and there's an activation function that tells me, okay, now send the message. And I'll send it along the axon. So this is like the cell of the neuron. These are the dendrites, and this is the axon. Okay? Once I fire a message, then the next layer will deal with it. And hopefully at the output I have that prediction. And we teach it, and I'll talk about how this learning happens. The old computers could not have enough of these, because the memory wasn't big enough. And we couldn't have enough of these layers with enough of these connections because we didn't have the power to calculate them all. Today we do. So these neural networks that have been invented in the 50s, now we call them deep networks because we can have more layers. Okay, that's what we call deep learning. It comes from the fact that we have many of these layers. This is a simple one where I had only 4 hidden layers. We call them hidden. The yellow ones are called hidden layers. And they're all fully connected. But there are other architectures because now we have these computers and we can do it very quickly. So we can experiment with different architectures. So there's what we call the fully connected, the convolutional networks. We have the recurrent networks, LSTMs, and all that stuff. There are many different architectures. But they're all part of the deep learning family. One thing I want to highlight here, because we're proud to be in Canada, fathers of this technology, and there are 2 of them, Yoshua Bengio, who's at the University of Montreal, and Jeff Hinton at the University of Toronto. I'll tell you a little bit of the story. I don't know if it's in these slides or other slides. The way it happened is because they were stubborn. When everybody dropped this idea about neural networks and were focusing on all the technologies, they kept on working on what they called later deep learning. And one day they were discovered, and that changed everything. Okay, now I'll mention that later on. But we're proud to say that this technology that is used everywhere in the world today, actually, it is thanks to researchers doing this fundamental research here in Montreal and Toronto. There are other people as well, like Yann LeCun, who's now the head of the AI team at Facebook, and Jürgen Schmidhuber, who's in Switzerland. They also work, actually Yann LeCun was a postdoc of Jeff Hinton, but these guys also worked on deep learning. So what happened? What happened is that in 2012, that's very recent, there's a competition of labeling images that have animals and objects. And so you have a collection of images, and you have to learn to predict what kind of object is in that image. So basically recognizing what's in the image. Okay. And there was a competition that many people were trying to beat. They had thousands of categories, like plants, animals, devices, food, structure, people, and so forth. And these images, you have to recognize them. So the accuracy of the techniques that were presented in every competition every year were reaching 70%, the year after 71%, 74%. There were improvements. They were using different techniques, sophisticated techniques. And then what happened, and just I want to show here that there was a measurement of the accuracy of typical humans. Typical humans would be between 85 and 90%, so we're still far away from what humans can do. And an expert human who knows exactly what the image is will reach a 95%, because these images are actually complicated to recognize because of the angle and all that stuff. So we're still very far away. In 2012, what happened is that two students of Jeff Hinton from the University of Toronto decided to participate in this competition, and they used their technique. Nobody knew about the technique. They used neural networks, actually deep learning networks that nobody was interested in, and they used GPUs to do that. And they jumped from 94 to 83. So 1 order of magnitude. People were surprised, there's something wrong here. What did you do? Well, we used this thing that nobody's interested in. We improved it, we call it deep learning. That's when actually Google was very interested by this, very intrigued. They called these students, they called Jeff Hinton, and they said, well, can we implement it now on our system? We have way more images, and they realized that actually it was impressive. So you have all these images that they get from online, and you can now automatically detect where all the cats are, the dogs are, and stuff like that, without a human checking them. So image recognition was completely changed thanks to this technology. And then because it was very successful there, this is a picture from Google at that time. Actually, they hired these students, and long story. They said, let's try them on other things. For example, speech recognition. Here's another competition from the 90s. So the DARPA funds typically military research projects. And here they have a data set of recordings, telephone conversations, and they wanted to automatically transcribe them from speech to text. Okay, so they can analyze the text. They can't ask people to listen to all these and type them, it takes forever. So they wanted an automatic way. And it was very hard, so they asked, okay, here's a competition, who can do that? And this is the switchboard data set. And many companies, these are different years and different techniques, and this is the performance. This is in terms of error rate, so the lower the better. You can see they plateaued, they didn't improve much. So in 2012, after they demonstrated that deep learning is working very well on images, they said, okay, let's use it on these voice recordings, and you can see they start going down significantly. That actually now, I don't remember here where the human performance is, they actually do better than humans at recognizing voice and transcribing it into text. So okay, let's try it into something else. These are different competitions. This is, if I remember well, detection of objects in images, not just labeling the images, but recognizing different objects. Also, we do better than humans. Then they tried it on translation. So they learn from pairs of sentences that are translated in 2 different languages. They learn how to translate. And you can see that it was stagnant, and by the time they started using deep learning, it started going up. We don't beat the humans yet, but the improvement is fantastic. Most of these smartphones that do translation automatically, now they use deep learning, and it's not that bad compared to what it used to be. Other techniques like visual question answering, so you have a picture, you ask questions about the picture, and then the computer has to answer. You have also humans that answer. This is the performance of the humans, this is the performance of computers getting there. This is question answering, you have text, okay, and then we ask questions, and the computer has to answer the questions based on that text, the content of the text. It's like in high school, what we do, the comprehension tests. And you can see that the computer is getting closer to the performance of the human. All that thanks to deep learning. So everybody's now is just talking about deep learning. And we think that that's a silver bullet. It can solve everything. Because people are only covering the nice stories. I'll show you some cases where actually it's not working. What do you see here?
A desert.
A desert. Who can see something else? Just a desert. Well, in the UK, the police was building a program to try to identify pedophiles and trafficking with decent pictures. And unfortunately, each time there was a picture of a desert, it's labeled as nudity. That's deep learning. Didn't work fine there. These are real stories. What do you see here? Who can tell me what's in that picture? What's that?
Car.
A car. You agree? What do you think a computer will find? Is that a car? We are humans. We can extrapolate and imagine actually I don't see the wheels, but yeah, it's a machine with two wheels and it's a funny car.
Looks like a Viewmaster.
Yeah, do you know what the computer will say? It's a horse. Why it's a horse? The logo. They go in the small details and say, tell you it's a horse. Okay, let's turn the car. Now it's clear. What do you see?
A car.
A car. Well, the computer will tell you, horse? Actually, no, horses. That's what deep learning will tell you. We also do description of what's in the picture. These are descriptions done by the computer automatically. Here that says a soccer player is kicking a soccer ball. Is he kicking the soccer ball? Not really. I don't remember the problem with this one. A street sign on a pole in front of a building. Yes, acceptable. A couple of giraffes standing next to each other. Are they standing next to each other? No. See, this one is big, this one's small. It's not that it's a baby, it's further away. So they're still not that good. This is the state of the art. What do you see here? A puppy or bagels? You can tell the computer will have a lot of trouble with these. Here's the typical one. Chihuahua muffins. A baby will be able to, a toddler will tell you, this one I can bite and eat, this one, no, it's a dog. Okay. The computer will have trouble with those. What if you have both of them on the same picture? It's not the only case. What do you see here? What do you see here? For us it's easy, but it's not that easy for the sophisticated computers we have. Okay. Now, here's another one very interesting. Actually, this is a panda, this is a gibbon, and if you take this image and the computer tells you it's a panda, and I have a confidence of 57% because it gives you the confidence level, okay? But it's labeled it properly, it's a panda. If you take this image, you add some noise in there, so suddenly it recognizes a gibbon with 99% accuracy. Not accuracy, confidence. So suddenly it's even more confident that it's a gibbon. Why? Well, just focusing here, I don't know. So there are many ways now people are researching how they can actually trick this deep learning to recognize something else. This is a famous picture where they add noise, but it's a picture of this funny, bizarre thing. Whenever they add it to another image, the computer thinks it's a toaster. So here, it recognizes a banana with high accuracy, and suddenly when I add this to the picture, the same picture, I just added this thing here, Then it says, oh, it's a toaster. But no, I'm not sure. It's not even a toaster, this thing. So people, of course, are tricking now the deep learning for face recognition and so forth. However, it's doing amazing things, though. Okay? Things better than humans in many things. So let's go to this machine learning and explain what this field, what does that mean? So machine learning gives means to the program, the computer, to learn from data, give it data that is typically labeled when it's supervised machine learning, and we interpret this data and by extracting some patterns from the data, and then we adapt to the data. What does that mean? Now, adaptation is actually prediction. I'm trying to predict what will happen. So basically, I'm learning from the data. The data is my experience. I learn that so that I can predict and adapt to this future, the world that is changing in front of me. It's, as I said, a field of AI, and part of machine learning. One subfield is called deep learning, but there are many other techniques. What I want you to remember is this picture now here. It's an animated picture. What I have in machine learning, I have data that is labeled. This is supervised learning. And the machine learning will go over this labeled data and build a model. Okay, that model now is represented as a cloud. I don't know what it is, it's fuzzy, it's just a representation of what discriminates between these classes. Then I will use that model that I learned. It can be many different things. It can be a neural network, it can be a decision tree, it can be different things. I will use that with data that hasn't been labeled, that I have never seen before, and it will label them for me. What does that mean, labels? So it means, for example, that I give it enough images with cats and dogs, and I'll say, this is a cat, this is a dog. This is a dog, this is a dog, this is a cat, this is a cat. Okay, and it learns from that, and then I give other images, and it will tell me by itself, that's a cat, that's a dog. Okay? And that's what machine learning is. So the model that I represented as a cloud is what discriminates the features in the image that discriminate between a cat and a dog, for example. Okay. We humans would say, well, the dog has ears that come down, the cat will have pointy ears, the dog doesn't have whiskers, or the cat has whiskers, whatever. I mean, we come up with features, we do it instinctively, we have it in our model, in our head. Well, that's what the computer is trying to do in machine learning. So as I said, that cloud can be a neural network, for example. It can be other things. It can be, that's what deep learning is. Deep learning is basically building the network with the different weights, such that when I give it an image, it will tell me with a good accuracy, this is a cat or this is a dog, or this is the answer, this is not the answer, and so forth. Okay, do I have a slide on reinforcement learning? No. Well, reinforcement learning, we here at U of A are known for reinforcement learning, and hopefully later I have a slide, I'll explain what it is. Reinforcement learning is also part of machine learning. What also you need to remember is that while deep learning is part of machine learning, and there are many other techniques in addition to deep learning, what distinguishes deep learning from other techniques, the old algorithms, is that the old algorithms, when you give them more data, this is a graph showing I'm increasing the amount of data that I provide to the algorithms to learn, and this is the performance, let's say accuracy. The more data I give it, the better it becomes. Then it reaches a point where the old algorithms hit a plateau. They don't improve. They don't know how to exploit the extra data that we give it. However, deep learning, the more data you give it, the more it learns. And that's why it reaches, if we have enough data, it reaches the performance of humans and it surpasses the humans. This is a very interesting characteristic of deep learning. But also, it also means that in order for it to work well, you need to give it a lot of data. So it's data thirsty compared to other methods. So if somebody has a very little data set for training, maybe deep learning is not the right way to do. Okay, so here's some examples. You all use an email system to receive emails. You often get spam, for example. Well, now, today, in email clients, we have machine learning that observes how you deal with your email, what you read and answer, what you delete without reading, and so forth, and it learns what you like and what you don't like, what is important to you, what is not important to you, and it learns what is spam and what is not spam for you, because what is spam for you may not be spam for somebody else. They may be interested in that. Okay, instead of writing rules, the machine learns by itself what is spam, what is not spam. The email system that you're using has machine learning in it without you knowing that. How does it learn? With labeled data. What is the labeled data? In this case, is your behavior. When you delete something and you read something and you store something, you are labeling the data indirectly for the machine learning. It learns from it. Other examples, when you go to the bank and ask for a loan, the person at the bank will ask you questions. You give a formulary, you fill in. Do you have a car? Do you have a diploma? Where do you live? And all that information is passed to the system. The system learned from previous customers based on their characteristics and based on the fact that they paid back or not. I can now predict what's the probability that you will actually default on your loan or you will pay me back. And then I will approve or not approve. So the bank, they use these systems already. Other examples, I mentioned the credit card. When you pass your credit card for an authorization, we use machine learning to predict whether this is a fraudulent activity or not. In medicine, and I'll show you many examples either this time or next time, in precision medicine, to do diagnostic, prognostic, treatment, recommendation, and so forth. We use machine learning. Here's an interesting example that you don't think about. This is a very interesting, well, it's not just a project, it's actually working, but this is a picture when it originally started at MIT. This is a student sitting on a wheelchair, taking the role of a paraplegic using this wheelchair, and they wanted to build a wheelchair that can work for a paraplegic, so they can't even use their hands to move this joystick to move forward and backwards. How can they operate the? Well, they can operate it with their brains. How? Well, the idea is actually quite simple. We ask the patient, after putting a helmet with sensors to get the brain activity, we ask them to do something that they actually can't do. We ask them to move a finger, move the right toe, or move your elbow or something. They can't because they're paraplegic, but they think about it. And there's a signature in their brain activity. They try to recognize that. Okay. Once they recognize that, they build this classifier from all the thoughts that they have. They will pick those cases when they actually, I detect this patient is saying move forward, because they associate, for example, the left toe to move forward, the right toe to stop, this elbow to turn left or turn right. And now, wearing this helmet, they can operate this wheelchair, okay, using machine learning. The same technology is also used for moving a cursor on the screen. So these paraplegic people can select a letter with moving the cursor just by thinking about it, and they can write to communicate. So it goes from spam and non-spam detector to something that can operate a wheelchair for a paraplegic. Okay. And you have all these applications in between. Everything you can imagine. Okay, this is what I mentioned reinforcement learning, and reinforcement learning is something completely different. So this is what I said at the beginning of class. I said we can teach this dog to walk again using reinforcement learning. So what is reinforcement learning? Reinforcement learning is not using this learning paradigm where I'm having a data set that is labeled and it learns from that a model and all this. That's completely different. It's based on behavioral learning. I try things. When they work, I do them again. If they don't work, I don't do them. It's like a child. You tell them, do that, and if they do that, they get a reward. If they don't do it right, they don't get the reward, or they get a punishment. Okay? If it works, because I get a reward, I'll do it again. If it doesn't work, actually not getting a reward, I will not do it. And the purpose is to maximize my reward. So a dog, a real dog, I'll tell it turn, turn, turn. It doesn't turn. I keep on saying turn, turn. The day it turns, nice, nice doggy, and I give it a treat. And it associates that with the, whenever he says turn and I turn, I get a treat. So they will do it whenever I tell them to do it, and because they want the treat. Okay? And that's how reinforcement learning will work. Okay? The agent, the software agent, has, I have another figure for it here. No. So the agent here, that's a software agent, I put a robot with its program, is faced with an environment, the world, and then has a collection of actions it can do. These are equivalent tools here. And at one point it decides to choose an action. And it does that action, and that action has an impact on the environment. The environment is changing. You have an observer, an interpreter, will say, actually, here's the new state of the environment because you did that action. And by the way, here's a reward. And the goal of that agent is to maximize the reward. So it will learn to choose the actions that will give it the maximum reward. So it learns a policy the policy is basically a sequence of actions that it has to take in order to maximize the reward down the road. So that's how the dog will learn. Okay? It will try different actions with this leg. Okay? And what is the goal? The goal is to move forward. And we give it a reward when it reaches that goal, walks forward. So the pioneer in reinforcement learning is Rich Sutton. I don't know if this year he was talking in his class. He used to have the time to talk to this class.
Maybe.
Maybe, we'll see. He's extremely busy, so he doesn't have the time to come. He works 1 day a week on campus. The rest is with Google DeepMind. But here are things we can do with reinforcement learning. You can teach a robot, like the case of this broken dog, a robot to do the best actions to do a particular task. This is an example where, and I think if Patrick Pilarski will come
Yes.
in this class, he will talk about these projects. In this case, is somebody who has lost a limb, and we add this artificial limb, prosthetic, and the artificial limb learns, using reinforcement learning, to adapt to the patient. So it's not just the patient adapting to this new artificial limb, but the artificial limb also learns to adapt to the person. And it predicts the action it has to do. Like you do unconsciously, if I want to grab this dog, I will not do this. That's what the typical robots do. Okay? I'm grabbing this dog, I'll go there, I'm already preparing my fingers to grab it. Because I predict that I'm grabbing this. And that's what reinforcement learning will do. These movements of the artificial limb will become very natural. So I want to talk about precision health. How much time do we have? We don't have much time. I can talk about this next time. And I want to open it to questions. Because people are listening.
Why don't we see what questions I have? We have 4 minutes. Questions?
Yes?
So earlier slides you mentioned why AI has seen a resurgence over these past few years, and one of the reasons was advancements in high performance computing.
Yes.
And regarding computer advancements and the future of AI, will there ever be a time where hardware has advanced given an X amount of years, because it takes time for things to progress, where there will no longer be a need to keep investing our time or resources to further advancements for this hardware, simply because it's beyond our human needs? So, for example, like you said before, 5 megabytes was something that was really expensive before, but now a single picture will be much bigger than that.
Yes.
Will there ever be a time where humans will say, oh, 20 terabytes, I'll never need that, and so we'll never keep on progressing past a certain point?
You probably know the famous quote by one of the founders of IBM, Watson, who, when they build these big computers, he said that, yeah, one day we'd probably need at least 4 of them in the United States. 4 of them? This is way more powerful than that computer, and everyone has it in their pockets. It's very difficult to predict what are our needs. So for example, you say, I actually don't need more than, if I have 128 gigs on my phone, I never fill it. So I don't need more. But if I tell you, oh, I can put cameras here, I can put all the different sensors that are collecting all sorts of data, suddenly, oh, I need more than 128 gigs. And people are building these wearables. So these are wearables, meaning yeah, it's technology you can wear, and they're collecting all sorts of data. Why do they put cameras? Well, I want to remember where I put my key. I can rewind when my camera and phone, whatever, taped, and I can see it. I want to remember what I did yesterday. I mean, people do crazy stuff. You don't know what your needs are. What are the needs? You know you can predict your needs tomorrow based on what you know today. But tomorrow there are other things. You create other things to create new needs. For some you need more. Faster, bigger, whatever.
Yeah. So continuing on that, will AI always just continuously need more and more as years progress and as it collects more and more data?
The faster and faster it gets, the more and more data it can process. And the more and more data it can process, the better it becomes. So I would say yes. We can do what we couldn't do yesterday, we can do today. But what we can do today, we'd like to do tomorrow.
Your question presumes a static definition of what human beings are. I don't think that's going to happen. We never have been static, really. And there's greater possibility of like machine enhancement of human brains and that sort of thing. So those things will greatly enhance what our computing needs are. So I don't think we're ever going to reach a plateau where we don't need any more ever. Yeah.
I'll give another example. Do you have a smartphone?
Yeah.
Okay. 20 years ago, if we asked you, do you need a smartphone? You wouldn't even know what it is. You don't need it. You can live without it. Today, you can't live without it. Can you live without a smartphone?
Guess not.
So we create new needs all the time, and then we can't live without it.
I was just reminded by your examples where the deep learning still can't get it right, still can't tell the difference between a dog's face and a muffin to a degree. When I see that, it just reminds me that the human brain may have a lot more going on than we give it credit for.
Yes.
And then when we're trying to estimate, when will convergence happen, that we might be wrong in that. So any thoughts on whether we fully understand the complexity of the brain and all this?
We don't understand the complexity. We know it's complex. And each time we think, oh, we got it right, we realize, no, it's not the case. We know, for example, that our neurons are not the same. Just recently, we learned that actually we have new neurons, even when we are adults. We thought that neurons, we are born with all the neurons and they start dying, we never have new neurons. Actually, it's not true.
Great news for the middle-aged.
Exactly. We build new connections all the time. The models that we have don't build new links. We design the network and that's how it is. The neurons are almost the same, but in our brain we have different kinds of neurons. The way it learns, and I'll explain it in the next lecture or the lecture after, it's just a question of changing the weights, so the importance of these links. Is it how the brain learns here? We do reasoning. We don't just propagate weights and that's it. How is the reasoning happening in that brain? We don't know. How we memorize things and then find them like this, we don't know.
Well, and the breadth of our experience.
Yes, I mean, how many times you were in the crowd and you recognize somebody far away that you haven't seen for a long time, and you just saw them from the sides. Oh, that's X, and you know that. It's phenomenal what happens here. We don't know how we do it. So we're still behind. But with this small, simple representation model of the brain, we can do amazing stuff. With the complicated machines that we have, the faster machines that will run faster and faster, we can try and explore other ideas. It doesn't have to be like the brain, but it can do better than the brain. So for a long time we're trying to mimic what the human does. It's not necessarily the right way to do it. We may create an intelligence from a different architecture, a different idea of storing and communicating and reasoning.
But ultimately, it has implications for whether our best creations become a tool or an entity.
Yes, definitely. I still believe it will be a tool because we're building it. We have to, from the beginning, learn how to make sure that we still have control over that. And it's a tool to do what we're doing, but better. Or things that we can't do them with this tool. Now, if we can from the beginning start thinking about creating them as a different entity, that's could be in a dangerous path. Because then we can lose control.
Could they simultaneously be tool and entity, or is that the equivalent of enslavement?
That's an interesting discussion. We can bring it up next.
We'll figure it all.
Yeah. Yes.
For the reinforcement learning, what is the reinforcement that the computer gets?
Reinforcement is the reward.
Yeah, but what is that reward? Like, is that a
In this
program
particular
that
case, it's
you
just
answer?
points, it's numbers. So it tries to maximize a number and you give it 1 or 2 or whatever you decide that reward is. Like in the case of the dog, you get a biscuit or whatever, that's the reward.
Yeah.
In the case of the agent, it's a number.
Oh, okay.
It's a real number. And it wants to have the maximum possible sum of all these.
And does it actually build new connections with
No,
the reinforcement
There's no,
learning?
actually there are people working on combining reinforcement learning and deep learning. But they're not really this connection as you think about, like in neural networks. This is more about, I want to learn what is the right action that I have to do at a given time. But the two technologies are being combined as we speak.
So before when you were talking about deep learning, you mentioned how there's neural networks and there's like more layers.
Yeah.
But I'm just confused about what you mean by that. Like, what is more layers? Like,
Okay. So in our brain we have neurons that are connected to other neurons that are connected to other neurons and so forth. There is a notion of input layer. So the input layer could be, for example, the retina. You get these images and the light, and then that propagates some signal that goes to my brain and I realize what it is. What is the output layer is not always easy to define in our case. But in an artificial neural network you have what we call an input layer where you give the data, and there's an output layer that gives you the output. In between, we create these hidden layers. So the information goes from the input layer to one hidden layer, another hidden layer, another hidden layer, eventually the output layer. Because the computers were not fast enough and didn't have enough memory and so forth, we couldn't build these very big networks. So some people actually tried to prove that having just one hidden layer is enough. So you have this vector coming in the input layer is represented in another vector in the hidden layer, and then you re-represent it again in the output layer, and that's what you try to predict. For example, the dog, cat, whatever. But it was limited, because you just have one hidden layer. With deep learning, we can add many, many hidden layers. Actually, you can have thousands of them, because the computers today allow us to do that. And by having these thousands of layers, some actually are even split in different blocks in the hidden layer, and so you learn more. You converge faster. You converge towards a better accuracy than with just one hidden layer.
So then at each layer, is it like gaining information? It's not the same information at each layer?
No, not the same information indeed. So there are examples with images, looking at the dog here. The first layer is trying to recognize, for example, there's a tail here, there's a head here, or just the lines, for example, just the structure. The second layer will put these structures together. The third layer will see the head and legs and whiskers and whatever. And then the last layer will say, oh, that's a dog. Does it happen like that in the brain? I'm not sure. Nobody knows. But in the deep learning networks, that's what happens. Yep.
So are we like pursuing AI in order to help us solve problems that the human brain is limited to? Because we just have built-in limitations. Like we haven't, like you said, we haven't understood the physiology behind the brain completely. It's still a mystery to us because it's, at the end of the day, it's a human brain studying the human brain. So they're at the same level, right? So how can one understand the other if they're both here? And then like AI would be here and just hit it from a totally different angle, and we would use that in order to.
So I don't understand your question. The question is, why do we do AI basically? Or
Yeah,
what
like
is
does it
exactly
have the
question?
potential
Because
to,
the AI, we do AI for different reasons.
like,
One is also to understand how we function, because we hypothesize and we try and see, well, maybe it works or it doesn't work. So many people are actually interested in AI to better understand the human being. Other people are interested in AI in order to build, as I said, a tool to do things that would take us too long, or we can't do, or we can do well. And then with AI, we can do it now and do it faster and more precise.
does it give us like a different perspective that the human mind would never reach, no matter how like outside of the box you are?
Possibly, yes. Possibly, because we are thinking about it and we can, as I said, hypothesize on different structures how we can do it, and because we have now the machines that can allow us to try these, then we can demonstrate if the hypothesis works or not. Now, if we build a machine that doesn't have necessarily the same way of functioning as we do, but is as smart, why are we doing that? Well, we're still trying to build a tool that is as smart so that it can help us as an extension of our own creativity. There are things that I wasn't able to do because I didn't have the time. Now this machine does it so fast that now I can do it. And it doesn't matter if it functions like my brain or it functions in another architecture. It's irrelevant in that case.
Could we ever get it to function as our brain if we don't even understand completely how our brain works? Like, we're applying the same kind of technology, like neural networks and everything, but we still don't.
So when we built the airplane, in the beginning, humankind was trying to mimic the birds, and they failed. They failed miserably for centuries. And now the planes, they fly faster than birds. They don't fly like birds. And the same thing can be applied to the brain. We don't have to really copy how our brain functions to build something that can actually be even better than the brain. The planes definitely fly way faster than the birds. They don't flap their wings. I don't know if I answered your question, but I hope the analogy can explain that. Other questions? Well, thank you very much.
Okay,
And,
great.
Thursday, I'll be here.